Okay, great. Thanks, Louis, for the introduction. Can everybody see my screen and hear me?
Yeah,
Hello?
everyone can hear
Okay,
you.
great. Thanks. Hello, everyone. I'm Haoshu, and today I want to talk about our recent work, operation, which is like a method to sensorize humans to collect data for dexterous humanoid manipulation. And right now, I am a postdoc at MIT, and starting next spring, I'll be joining the University of Maryland as an incoming assistant professor. So in today's talk, I will focus on like introducing how we can sensorize, for example, myself in this video to like conduct some daily manipulation, collect those data, and transfer them onto a real robot. Here, like an Unitree H1 robot to solve the data problem in humanoid dexterous manipulation. So before I talk about our method, parry operation, we need to go through the data challenges nowadays. So we all know that data is a huge bottleneck, especially for robotic manipulation. And when we are talking about data, they usually include observation, which are vision, tactile, proprioception, and action, which are like usually they are 7 to 60 degrees of freedom. So we usually need to collect the data set that consists of a sequences of state action pairs. And nowadays, there are three common ways to collect the manipulation data. They are simulation, video, and teleoperation. So for simulation, we have seen a huge success, especially in humanoid locomotion, right? But when it comes to manipulation, it's actually pretty challenging because just imagine how many scenarios we have. For example, we need to do part assembly, we need to do housekeeping, and it's actually pretty painful to transfer all those scenarios into a simulator. And even if we are able to do that, the sim to real gap is also large for manipulation. So these two bottlenecks make this method more suitable for, makes it hard to scale across different tasks. And some people might say maybe we can learn from online videos. So the problem of learning from video is that they only contains visual observation. But for manipulation, we need like many other perception modalities, including tactile, force, and other sensors. And online video, they also doesn't have accurate action data. Some people might say we can recover the actions from post estimation, but they are usually not accurate enough. So these two problems make it more suitable for pre-training. And lastly, teleoperation. So for teleoperation, the data collected during or before training would be the same as the data we used during testing. So this feature makes it very popular because there is basically no embodiment gap. However, we all know that teleoperation is actually expensive. And sometimes it's even limited in capability because the human teleoperator, they don't feel what the robot feels. For example, they don't have touch feedback. So these features make it inefficient for scaling up the robot data. And I feel like we really need a new paradigm here. Then I start thinking like how we can really uh, break the wall of data nowadays. And then when I look at myself, I realize one thing, which is for us humans, we are actually doing manipulation every day. And it means that the data is generated, but the big problem is they are not recorded. What if there's some way that can record our daily observation, not just visual observation, but also like tactile information, and also our actions? Then we can use this data to train a policy and probably deploy the policy onto a humanoid robot. So we call this paradigm parry operation. And it means that we want to build devices that can sensorize and records human manipulation. While also we want to maximize the transferability of the data to real robots. So the reason we call this parry operation is because parry is contrasted with tele in Greek. So we want to use this term to emphasize that we are actually building devices that humans can directly wear and sensorize our manipulation instead of like remotely controlling a robot. And I would also like to say, I think parry operation is inherently suited for humanoid dexterous manipulation. Because one of the reasons that we built humanoid is because we want to decrease the embodiment gap of the robot and the humans so that the data generated by human can be transferred to the robots. And in today's talk, I'll cover our recent works in this direction, which include both arm exoskeleton and hand exoskeleton to capture both arm motion and hand motion. So let's start. The first part of my talk is about arm motion recording. And when we talk about arm motion recording, some people might say, oh, you just need to capture the end effector. But that's not true that's not enough in some cases. In our daily manipulation, sometimes we'll need to use our forearm and chest to conduct like whole body manipulation, including hold babies or like carry heavy boxes. And sometimes we want to regulate the position of our elbow. For example, when we are carrying some objects with both of our hands, but we need to close the door, we can use our elbow. So given these two scenarios, we try to like build some arm exoskeleton. Here we call it air exo, to capture the arm motion when we are doing daily manipulation. So Air Exo is an open source and portable, inexpensive exoskeleton. The idea is that instead of having actuators at each joint, so we develop some low cost and modularized joints that only has position encoders inside. And with this kind of a modularized joint encoders, it makes the building of such exoskeleton very cheap. So we just need about $300 to build exoskeleton for one arm. And with the modularized design, it's also very easy to adapt our exoskeleton for different arms. Here we list UR5, Franca, Kuka, and of course we can build it or adapt it to different humanoid robots. And it's also very like light, so you can wear this kind of exoskeleton. And with this kind of like Air Exo, you can just mount some cameras on top of the exoskeleton to serve as the global camera. And when you do daily manipulation, you can record the data. For example, here we showed some video action paired demonstrations we collected. And besides the videos, we also record all the joint angles. And now, can we just use this data to train a policy? Well, sometimes we could, but there's still some problems. Here we show the biggest challenge, which is there's still some visual gap between the data we collected and the data that the robot will actually see during evaluation. So we can see clearly that when we collect the data, it looks like something on the top. So the visual observation is very different from that of the robot. Some people might say, well, if you properly set in-hand camera, then there might not be any visual gap. That's true. However, the problem of using in-hand camera, like in the case of the UMI gripper, is that only the in-hand cameras could sometimes degrade the performance of the policy. And here we give an example. So for the task of collecting toys, we try to mount different cameras, including one global camera and two in-hand cameras at the wrist. So we found that given the same demonstrations and same number of trajectories, if you just use one global camera and train a policy, the success rate is about 45%. But if you just use two in-hand camera, the success rate could increase to about 60%. And eventually, if you combine a global camera and two in-hand camera, the performance could goes to like about 72%. And it shows that adding a global camera can increase the performance. And this comes with no cost, right? So this is the scenario for 2D policies. And nowadays, there are also more and more 3D policies that takes point cloud as input. And for this kind of policy, a global camera is even more important because for an in-hand camera, when it's too close to an object, the depth perception will fail. So given these two reasons, we say a global camera is definitely needed. Then how could we conquer the challenges of the visual gap? So we propose visual adaptation. And the idea is nowadays there are many AIGC techniques. So we could use this AIGC technique to transfer the images taken by our exoskeleton to the images that the robot will actually see during evaluation. For example, if I didn't tell you, can you see like this image is actually generated by like an AI? So it's actually not taken by the real robot. And this is actually what the robot looked like previously. So in this image, you could see the human hand. And you could also see the exoskeleton. And then we can use SAM to segment, for example, the human hand and exoskeleton and remove these two objects using some image inpainting technique. And later, remember that we also recorded the robot joint using our exoskeleton, so we can render some robot image. But it's still not very realistic, right? So we train a control net to generate like realistic robot image based on the rendered robot image. And then we transpose these these robots onto the background. And here is the process of how we get the images that can fool the policy and deploy for the real robot. And here I give you more examples. So on these examples, the top video is the exoskeleton captured data, and the bottom video is the retargeted or adapted video for the robots to learn. You could see that there is still some artifacts. The reason is that we didn't add any temporal smoothings for the visual adaptation. And following similar pipeline, we can also adapt the depths from the exoskeleton data to the robot data. And then by combining the adapted video data and depth data, we can generate, for example, some fake data, but that looks very vivid for exoskeleton collected data. And later we try to train a policy given only the exoskeleton data. So we collected 50 demonstrations using our AirExo, and we trained policies for 3 different tasks, including collect toys, lift plate, and open lid. And for this task, we compare the policy performance with the policy trained with teleoperation data. And we could see that the performance of parry operation is actually pretty close to the performance of policy collected by teleoperated data. And I would also like to emphasize that this is actually not a fair comparison. Why? Because parry operation, with parry operation, you could actually collect data much more efficiently than teleoperation. So if you think about it in this way, then we can conduct another comparison. And here, for the x-axis, it denotes the data collection time. And for the y-axis, it denotes the policy performance. So we could see that for the policy trend with parry operation data, which is the green curve, it's always better than the policy trend with teleoperation data, given like different amount of times. So this emphasizes that parry operation is actually a pretty promising way that we can scale up data at a large scale. Okay, so just now we have introduced parry operation for the arm motion, which where we build arm exoskeletons to capture human motion and joint angles. And we introduced how we adapt visual observation from exoskeleton data to the real robot data. Any questions so far? Okay, if there's no questions, then let's continue. For the next part, I'll introduce our hand exoskeleton. So before I introduce that, let's look at some humanoid videos. So this is an video from Tesla, and we could see many dexterous manipulation that the robot used their hand to do different tasks. But if we look at these examples carefully, we will notice one interesting thing. In all of these videos, the Tesla bot is actually using their hand just with open and closed motion. So there is actually no dexterous in-hand manipulation. That's a little bit frustrating, and I call this dexterous dilemma. It means that nowadays many robots, although they have a humanoid hand, they often use it as a big gripper with just open, close motion. However, when we build like a dexterous hand with so much money, what we really want is we want it to show some truly dexterous task, which is beyond what a gripper can do. For example, we want to use the hand to manipulate some articulated objects like a paper cutter. We want to rearrange object in our hand, or we want to manipulate some small objects like nuts and bolts very fast or in a very efficient way. But all these tasks, they are actually very challenging to collect data for because with just teleoperation. And the reason is that they all require very precise and fine tactile or haptic feedback to humans. So by teleoperation, we actually don't have very good haptic feedback. So you basically cannot see any like kind of very dexterous data conducted by teleoperation. And in today's talk, I would like to introduce Dexop, which is a hand exoskeleton that can collect real-world dexterous manipulation data with direct feedback from the passive robot hand to human's hand. So I will introduce 3 topics about dexterous parry operation, including what is needed to build a good device and how we can achieve that. And lastly, why is it better than teleoperation? So what is needed? Well, recall this figure that when we talked about data, there are 2 kinds of data. One is observation. And in terms of observation, we all know that visual perception is very important. But beyond that, tactile is another very important modality. Here I would like to show you a video. In this video, a scientist injected some drug to a human's hand, and this drug would numb the sense of touch of the human, but the human can still move their hand freely. So we could see that without the sense of touch, it actually took the human over 30 seconds to accomplish a very simple task, which is striking a match. And this video emphasized how important it is to have tactile feedback when we are doing our daily manipulation. In terms of action modality, beyond position, another important modality is torque. So imagine when we are holding a bottle, if we just shape our hand to that pose, but we are not applying any force, then the bottle will just slip from our hand. And it emphasized that torque is another important modality when we are capturing data. So lastly, we need to keep in mind that for the data collected by peri-operation device, it ultimately needs to be deployed on a real robot. So we need to build some devices that can mitigate the gap of human and robot hand. And given all these requirements, some people might say, can we use a tactile glove to record human tactile data and train a policy? Well, there are several drawbacks of using a simple tactile glove. The first one is that there is always some mismatch between the robot hand and the human's hand. For example, different humans have different size of hands. And also, like the robots, it might not have the same kinematic chain as the human hand. So any mismatch of the human and the robot hand could make the learning harder. So that's the first drawbacks. And secondly, these tactile gloves, they usually provide low resolution tactile sensing. For example, for this glove, it just have about or less than 20 taxels on each fingertip. But for humans, we actually have over 300 tactile receptors in just one fingertip. So it's a open question that whether this kind of low resolution tactile sensor is enough to support our daily manipulation. And lastly, there are some high resolution tactile sensor, including vision-based tactile sensor or Hall effect-based tactile sensor. But they are usually pretty bulky to wear. So given all these problems, we argue that tactile glove might not be a good peri-operation device. Then how can we build devices to capture data for hand manipulation? Because it sounds like a very hard problem. On one hand, we will have constraints from the human, and on the other hand, we will have constraints from the robot. So since probably we couldn't alter the human hand, like cut off some fingers to adapt to the robot hand. So we need to start from the robotic hand. And I argue that we need to do some co-design of the robotic hardware with the peri-operation device. So the first thing we did was to build some robot hand that's closer to human's hand. In our recent work, Eyesight Hand, we focus on three aspects. The first aspect is we try to make the tactile sensing of a robot closer to that of the human's hand. In Eyesight Hand, we incorporate a whole hand tactile sensor, and it also has pretty high resolution. It's vision-based tactile sensor for the whole hand. So we do not only cover the fingertip, but also the palm and other segments of the hand, so that the robot could feel very fine geometry when it interacts with the environment. The second thing is we try to make the dynamics of the robot hand closer to that of the human's hand. We incorporate proprioceptive actuator so that the robot can be very compliant when it's interacting with the environment, and the robot can also move pretty fast, like to catch a flying bottle. The third thing is we try to make the form factor of a robot, of the hand, closer to the human's hand. So you could see that eyesight hand, it actually follows the human hand kinematics. It has 7 degrees of freedom, so that, so you can teleoperate it easily. But teleoperation is not what we want, right? Our goal is to build peri-operation device. And after we have eyesight hand that's pretty close with a human's hand, such kind of peri-operation device is becoming easier to build. We just need to bridge the human hand and the robot hand. So here is how we did it. We took the model of an actual robot hand, and then we removed all the actuators, which is enclosed by orange circles. And then we put joint encoders or position encoders at each joint, which is highlighted in green circles. And for all of these passive hands, we then build a wearable exoskeleton that has the same kinematic chain as the passive hand, and humans can also put our hands into this exoskeleton. Then we connect the wearable exoskeleton with the passive hand by some linkage system. And this linkage system, it allows humans to actuate the passive hand with our own hand. And it also transmits forces from the passive hand to our hand. And now we have a device that can capture human hand pose, and the passive hand can interact with the environment and capture the whole hand tactile sensing. So in this video, I illustrate the data collected by our device. You could see that it captured hand pose. So thanks to the joint or position encoders at each joint, you can capture the hand pose with very high frequency. And secondly, it captured the whole hand tactile sensing. So in this example, we are holding a textured ball, and you could see the texture at different position of the hand. Okay, so with this kind of device, you can actually do many dexterous manipulation. So for example, you can use it to screwing small nuts and bolts, where in this example, you need to use your index and thumb to rotate and screw the cap. We also show that you can do in-hand reorientation. So this manipulation is actually pretty challenging because you definitely need good haptic feedback. And this kind of in-hand reorientation is hard to achieve by teleoperation. But here you could see that with hand exoskeleton, you can reorient a park easily. We also show an example of operating a syringe where you need to also reorient the syringe into a pose that you can use your thumb to press it. So beyond precise manipulation that just involves the fingers, Dexo can also allow humans to do whole hand manipulation. For example, you can flip open a seasoning bottle where you need to use your index and middle finger, as well as the palm to secure the bottle, and use your thumb to open the lid. Another example is using the paper cutter. So you need to press the handle to release the blade of the paper cutter with both index, middle finger, and the palm. And then you can use the paper cutter to cut the paper. Okay. Previously, we showed some qualitative examples of DHM doing some dexterous in-hand manipulation. And here we try to compare DHM with teleoperation. So for this simple task of box packaging, we found that it's actually very efficient to collect data with DHM. It just took us about 10 seconds. But if you want to do the same manipulation with teleoperation, it actually took us over 70 seconds. The reason is that the lack of tactile feedback makes it very hard for humans to decide what to do at every minute or every second. So we invite 4 different users to conduct comparisons on 6 different tasks, including bottle opening, bulb installation, box packaging, and drilling, hard disk assembly, and cardboard folding. So for the first 3 tasks, DHM can achieve 2 to 7 times more efficiency than teleoperation. And for the latter 3 tasks, the teleoperation cannot even accomplish the task. Okay. So right now, we have introduced exo, the arm exoskeleton, and DHM, the hand exoskeleton. So when you combine air exo and DHM, you end up having a whole upper body exoskeleton. And now you can finally use it to collect data for humanoid and do humanoid peri-operation. So here I show you an example of me doing peri-operation with this full upper body exoskeleton to collect data for a task, which is bulb installation. So at the left side, I showed some observation captured by our system, including visual observation from both wrists and tactile observation from both hands. And in the right side, I showed you the joint state captured by our whole body exoskeleton. So there is no retargeting. We just replay the joint signal from the position encoders. And with this kind of data, plus a little bit teleoperation data to fix or to mitigate for some assembly error when we were building the arm exoskeleton. Now we can train a policy that's deployable to a real robot. So in this example, you could see that the Unitree H1 is trying to assemble a light bulb, and it's continuously doing this process. And we could see that the policy is actually robust to errors. So for example, here, oops, it failed, but then the robot would repeatedly try to recover from this kind of failures. Oops, bingo, is success. Okay, and here is the comparison of our policy trained with peri-operation data against the policy trained with only teleoperation data. So surprisingly, we found that with peri-operation data, which means the exoskeleton collected data, the policy is even better than the policy trained with only teleoperation data. But usually people consider teleoperation data as a better sources for data because they think there's completely no embodiment gap. Then how could our policy be even better than that? So we found that for this stage, stage 4, for the transition from stage 4, which is bulb installation that require the robots to screw the bulb, and stage 5, which is the robot need to grasp the lampshade and cover the bulb. So for the transition between these 2 stages, the policy trend with teleoperation is struggling to transit from the previous stage to the latter stage. And we try to understand why is that. So we visualize the data, like the data collection time at each stage. And we found that, so for teleoperation data, because the human doesn't have any haptic feedback, so it's hard for the teleoperator to tell if the bulb is tightened. And in that case, the teleoperator would tend to like over rotate or over screw the bulb so that they actually spend a lot of time here, like 38 seconds for this stage. And this results that the data set is actually biased toward this stage. And as a result, the policy would tend to like stay in this stage instead of transit to the next stage. This is actually an interesting finding, and it shows that without proper feedback to the humans, sometimes we could actually introduce some bias in the data we collected and eventually degrade the policy we have. Okay, so as a recap of my talk, today we introduced arm exoskeleton and how we can adapt the visual data from this kind of arm exoskeleton to a humanoid robot. And then we introduced Dexop, which is a new way that we can collect like dexterous hand manipulation. And eventually we can combine all these components and build humanoid peri-operation device. So what is not covered in today's talk is like locomotion. And that will also be our future work. I believe that you can like capture the human like trajectory by some either leg exoskeleton or just some high-level IMU data that only tracks your global position. And then if you combine that with some robust low-level controller, then you can probably achieve like whole body local manipulation. Yeah, and that's all of my talk. Thanks. I'm happy to take any questions.
Does anyone have any questions? Yeah.
Can you hear me?
Yeah, I can hear you.
Thank you for the talk. I really like the Dexop work, but I'm also curious how usable it is as sort of different user. Personally, tried some other exoskeleton hands, and I figured researcher who designed it can use it, but sometimes when I try, it was like way too uncomfortable or super difficult to use. So
yeah, that's a very good point. That's a very good point. I also tried some other exoskeleton, and I found the same problem. So one good thing about Dexop is, 1 second. So one good thing about Dexop is we completely decouple the passive robotic hand and the human's hand. So this brings two advantages. One is that we can actually have many advanced sensors on the passive robotic hand part. The second thing is for the human exoskeleton, it's actually pretty lightweight. So there's not much constraints. And I don't know if you could see the finger cots here. 1 second. So if you look at the human exoskeleton part, it just has one finger cots that fix the human finger. And this fingertip cot is also adjustable. So you can adjust the position of this fingertip cot to adapt to different finger lengths. And as a result, there's not much linkages here. So nothing will block the movement of your hand. And you can also adapt to different humans' finger lengths easily. So we actually tried with different human subjects, and we found it actually very easy to wear for different humans.
Oh, thank you.
Yeah.
Would you like to reduce the dependency on mixing teleop data, or do you think the teleop data still provides important information?
Oh, so the question is about whether teleoperation data is still important in this case. Yes. So you see that for our experiments, we use both perioperation data and teleop data. And the reason we use teleop data here is because there are two reasons. One is when we assemble the arm exoskeleton. So since we assemble it in-house, there are some errors introduced by, for example, when we cut the carbon fiber or when we assemble different parts or when we calibrate the sensors. So these kind of small errors is actually hard for us to solve in a lab environment. So maybe people could solve it in the future, like in some big companies, but it's hard for us to solve it by just in our lab. So we use some teleoperation data to mitigate the small like calibration error. So that's one part that teleop data is still important. And another part of teleop data is you can use it to recover the false information. So for our periop data, we just capture the state at every moment, and then we need to use it to recover the action information. So that kind of action recovery will require you to basically like recover the force at each joint of the robot. And such recovery is also like a little bit complicated because you need to calibrate the force sensor. So if you want to avoid such kind of tedious work, you can use some teleoperation data. But I would say eventually all these problems could be solved if you have very good hardware manufacturing experience. And also like in someday, that's something we're gonna solve. So I hope eventually we can get rid of teleoperation data completely. And that we already showed it in the arm exoskeleton example. So the next step is to also remove the teleop data in the hand dexterous manipulation.
Cool. Let's thank the speaker again.